So for graphing these reciprocal trig functions, we'll start with cosecant, which is 1 over sine. And on the paper that you have, you've already got the graph of sine, and this is just a review of the steps that we take. So we draw our original function, and that's already been done for you. So sine of x is already there. Then you complete the steps for the reciprocal graph. And although on our paper yesterday we had 6 steps, we sort of summarized them into 3 steps. Draw your original function first, which is already done for us. Number 2, do all of your asymptotes, vertical asymptotes and horizontal asymptotes. And then number 3, plot whatever points that you can and draw your graph. So, first step is done. Our graph is already there. Second step, draw your asymptotes. Where do you have vertical asymptotes? Sorry? Where do we have our vertical asymptotes? Wherever we had x-intercepts, right? Because the y value at an x-intercept, if I look at this original point right here, 0, 0, or this one at pi, 0, the y-coordinate is 0. And if the reciprocal graph changes every y-coordinate to 1 over y, well, whenever we have 0 for y, we're going to have a problem, because 1 over 0 is a non-permissible value. So we have vertical asymptotes whenever we have x-intercepts. So we're going to have a bunch of them here. Negative 2 pi, pi at 0, and we can label them all x equals negative 4 pi, x equals negative 3 pi, and so on. So we notice that our asymptotes for cosecant are exactly at the same place as we have zeros for sine. If we wanted to write the equations of all the asymptotes all at once, how would we write that? Do you remember how you wrote the equation for all of the zeros? Yes. Yes. So it would be k pi, where k is an integer, because k can be any positive or negative whole number. We can also, well, let's finish our graph, and then we'll look at domain and range as well. Anybody else need the paper? So now the last step for graphing a reciprocal after you've done the asymptotes, oh, we should look, does this one have a horizontal asymptote? No. And the reason it doesn't is we have a horizontal asymptote in a reciprocal graph if your original graph either goes up forever to get really, really large positive y values or goes down forever to get really, really large negative y values. But in this case, the sine graph stays between negative 1 and 1. So now we start picking some points. Can someone tell me one point on this graph besides the zeros? For example, what point is this? Pi over 2 comma 1. What's going to happen to that point when we do the reciprocal, when we change the y value to 1 over y? It stays the same. Does that make sense for this point, and this point? And down here, what's this point on the graph? Something comma negative 1. What would the x-coordinate be? Yes, negative pi over 2. And what's going to happen to that point? It stays the same. And that's going to happen for all of these points at negative 1. Now I'm going to put one more point on our original graph. Something comma 1/2. I want you to tell me what the x-coordinate is. Pi over 6. Where is that point going to go? It's going to go up. If we do the reciprocal of 1/2, what are we going to get? 2 over 1. So we're going to have the point pi over 6 comma 2. Now, every place where the y value is 1/2, does it make sense that it's going to become 2? So here is another y value of 1/2. There's another place that it's going to be 2. And this section is going to look like this, going towards the asymptotes. In fact, all of these sections up here are going to look like that. And similarly, if you did the same thing on the bottom sections, you'd have a bunch of points on your original graph where it was negative 1/2, and that point's going to change to negative 2 over 1. And so all of these bottom sections are going to look like this. And the green graph is the graph of cosecant of x. So now if we look at our green graph, could you tell me the domain of our green graph? X cannot equal k pi. So everywhere we have an asymptote is a non-permissible value. So we say x cannot equal k pi, and then we have to specify that k is still an element of the integers. And our range? Close. Be less than or equal to negative 1, or y would be bigger than or equal to positive 1. So now we can graph all of our trig functions. We know our regular ones, sine, cosine, tan. And if we apply the rules, we can get our graphs of cosecant, secant, and tangent. So I would like you to try the secant one on your own. How did you do with the graphing? So now, everywhere where we have an asymptote is the same as one of our zeros of cos. So if we wanted to write all of those equations of all of those asymptotes, do we remember how we wrote the zeros of cos? X equals. Notice that they're all the odd numbers times pi over 2. And when we wrote this for cos, we had two different ways that we wrote it. Do you remember one of the ways to write all the odd numbers? Times pi over 2. It's a good review then. So one of the ways that we can write odd numbers is 2k plus 1. Because 2 times any number will make it even. And then if we add 1, we'll make it odd. So if I go 2k plus 1 times pi over 2, where k is an integer, that will be all the odd numbers, positive and negative, times by pi over 2. The other way that we wrote it was by starting with one of them. So if I start with pi over 2, because that's sort of my first positive one, and then I say, what is the distance between our asymptotes? It's a distance of pi. So if we start with pi over 2, and then we add pi, k pi, as many times as we want, that will also get them all. Because we started with one of them, and then we just jumped by pi's, both in the positive and negative direction. So if you were asked to write either the zeros of cos or the equations of all the asymptotes, those are 2 different options that you have. Again, for our domain then, it's going to be exactly the same thing. You can choose either one of these and say x can't equal all of those values because those are our non-permissible values. And our range is identical to our cosecant range. Now the last graph that we're going to do is our cotangent graph, and this one is going to be the busiest looking on your paper when you're done, because it's already busy. Tan is busy because it has a bunch of asymptotes and a bunch of lines to begin with. So if we go through the steps, wherever we have x-intercepts, we're going to have asymptotes. So we're going to have an asymptote here, here, and so on at all the multiples of pi. And if we label them, we've got x equals negative 4 pi. Well, that's too far. Okay. X equals negative 3 pi. X equals negative 2 pi. X equals negative pi. X equals 0. X equals pi. 2 pi. 3 pi, and so on. Now, this is where the graph of cotangent doesn't quite follow the rules perfectly for our reciprocals. Because our reciprocal, next thing we would look at is our horizontal asymptote, and the tan graph does go up forever. So according to that, we should draw a horizontal asymptote at y equals 0. But it's all on how they've decided to really define cotangent. Because cotangent is 1 over tangent, but from your identities, what also do you know cotangent is equal to? It's equal to cos over sine. And so because it's equal to cos over sine, wherever sine is 0, which is at all of our multiples of pi, we have our asymptotes. But what happens at pi over 2? Well, if the definition of cotangent is 1 over tangent, then since tangent doesn't exist at pi over 2, cotangent shouldn't exist at pi over 2. But if the definition of cotangent is seen as cos over sine, what happens at pi over 2 for both cos and sine? What is cos of pi over 2? Think about your pi plate. Cos is your x coordinate. Pi over 2 is at the top. Your x coordinate would be 0, because the coordinate would be 0, 1. So if you thought about cotangent as cos over sine, then at pi over 2, cotangent would be equal to 0. So now we have a dilemma as mathematicians. How should we define cotangent? Should we define it as cos over sine and have that value be equal to 0? Or should we define it as 1 over tan and say, no, it doesn't equal 0, and we're going to have an asymptote at 0? So it's decided that they're going to think of it as cos over sine. So at all the places where cos is 0, cotangent is 0. And so at all of these asymptotes, instead of them being also non-permissible values, we're going to think of them as equal to 0. There's a point on our original tan graph. Can you tell me the coordinates of that point? Can you tell me one of the coordinates if you can't tell me both of them? Close. It's going to be pi over 4, comma 1, because tan of pi over 4 is equal to 1. So this is saying, now if I haven't studied my pi plate for quite some time, I do need to have it memorized for my final exam. So that might be something you'll want to work on in the next 8 days. No, is it 7 days? 7 days. And what's going to happen to pi over 4, comma 1 when we do the reciprocal? It's going to stay the same. In fact, everywhere where your graph has a y coordinate of 1, it's going to stay the same. What's the other place that your graph stays the same? At negative 1. So everywhere where we have negative 1, it's going to stay the same. So step 3 when graphing a reciprocal is do a bunch of points and then graph it towards your asymptotes. Let's look at the first section on the far left here. Can you see you have 3 points in between 2 asymptotes? Does that make sense? It goes through those 3 points and it goes towards your asymptotes. In fact, it's going to do that same thing over and over again. And that green graph is our graph of cotangent. What's your domain going to be? Everything except for k pi. What's your range going to be? Y is an element of the reals. It's everything. So those are your reciprocal graphs: cosecant, secant, and cotangent.